Okay, so today's topic is so-called streaming algorithms. Maybe not as you think in Netflix, but I'll try to motivate this area of algorithms research, and particularly here, randomization is kind of key in almost all the known algorithms. So we call them streaming algorithms. Streaming algorithms. And today, and also next time that I'm lecturing, we'll be talking about so-called streaming algorithms. Today, we'll look at one particular problem called frequency estimation, which is perhaps less exciting than the next one, which is called heavy hitters, but we'll use the solution from today to solve the problem next time. I mean, the next problem is a bit more natural, perhaps. But in general, in streaming algorithms, we assume that the data that we process is somehow divided in a data stream. So the items are coming one by one. So that's kind of the idea. So we have a stream of items. So for now, maybe we can just think of them as x1s to xn. Each of them come from some universe. Maybe we can also just think of them as integers in the range 0 to u minus 1. So here the idea is that we see the items one by one, and then we want to compute some kind of statistics on this data that we've seen. For instance, very natural problem is frequency estimation that we will look at today or solve today. So in frequency estimation, the goal is to answer queries of the form given an index I in this universe, estimate, compute estimate, write it like this. An estimate, let's write it as f hat of I. And here it's an estimate of what? It's an estimate of fi, frequency of I, which is the number of items in the data stream equals I. Makes sense? So I have a data stream of n items. Each item comes from the universe U. The frequency of I is the number of these items in my stream that is equal to I. Right? So the stream could be, like if I had a stream, say 3, 1, 1, 2, 1, 4, then after processing this stream, the frequency of 3 is 1. The frequency of 1 is 3, and the frequency of 3 is also 1. Right? So there's just a number of occurrences of a given item in the data. This seems like an easy problem to solve, right? You just store a hash table, a hash map. Whenever you see an item, you put it in the hash map if it's not already there, right? So you can store, for instance, the key value pair. I have now seen one occurrence of the key 3. When I see the next item, I've now seen one occurrence of the key 1. When I get another one, I check, do I already have this key in there? If I have, in this case I do, I just increment the counter. Now I've seen 2 1s, right? And then I can keep going, right? So then I see a 2, so I put 2 with a count of 1 in my data stream. I see another 1, so I just update this counter. And I see a 4 with a count of 1 now. Right, so it's an easy problem to solve. I just put it in a hash map. And then when I want to estimate the frequency of the item 1, I just look up in the hash map and return the counter. And if there's no such counter, I return 0. Right, so what's the interesting part about this problem? The problem is the idea is we would like to use space much less than the length of the stream. So you could imagine, I guess one prime use case of this is, again, we had this example last time, if maybe you're maintaining an internet infrastructure, so you're forwarding pages across the internet, and maybe you want to keep some statistics about what's happening. For instance, you want to know, is some IP address seeing a lot of traffic? So maybe you can keep track of how often is one concrete IP address being the destination of a package. You can just count that, how many times you see a package going there. And then it makes sense to, perhaps you don't want to store account for every single unique IP address that you saw, in particular if you have some small hardware that doesn't have a lot of memory, maybe you want to use less than linear memory to store it. So that's the general idea in streaming algorithms, is you want to use sublinear memory. Right? So sublinear memory in particular, we often want to use much less than linear. Typically, our goal is to use something like, say, we have a linked n stream, maybe we want to use something like log n memory, or maybe log n to a constant memory, something like this. We want to use much less space than storing the whole stream. And I think it's not too hard to convince oneself that that means that these estimates will not be exact. If I cannot store everything I see, I'll probably have to settle for some kind of approximation or mistakes in the estimates I'm getting. That makes sense? So particularly here, we want to use, by sublinear here, we want to use, so that two things, right? So there's the length of the stream n, so we want to use little o of n memory, and we also want to use little o of the size of the universe memory. Of course, you could also solve it if the universe is small. We also know that there will never be too many entries in this hash table, right? There'll only be one for every universe. There'll also only be one for every item in the data stream. So you can have solutions that use around n space or u space, depending on. Okay. Let me say that some of the reading material in this area, it varies a little bit how they measure space. Some measure space in number of bits, and some measure space in number of machine words. And it actually is quite a difference. If your space usage is around log n, there's a big difference between log n bits and log n words. It's like maybe a quadratic difference in many cases. So people in this research field really care about how many bits you're storing. For us today, we're just going to measure space as we normally do, and how many keywords, how many. It won't be that important. I think for us, the most important thing is really how do these data structure streaming algorithms work. But this is the overall problem. This frequency estimation. We have a stream of items, and we want to estimate how many times did I see a given item I. There are, yes, a couple of popular models that we can study the streaming algorithms in. Let me maybe put them down here. So there, I guess there's three different setups that are typically studied. We start with the simplest one, which is called the cache register. Register. Sometimes it's called insertion-only. So in this model, it's basically the one I saw up there. You basically only get items, and whenever I see an item, the frequency of that item is incremented by one. Right? So that's a simple one, insertion-only. Then we'll see if you want to say, what if I can also support subtractions to my frequencies? Then we have two different models. One of them is called strict turnstile. Name turnstile. And the last one is just called turnstile. So this one is really like here, every frequency is always updated by one if I see an item I. In this one here, an update is both an item. So here updates. They are pairs I and the value delta, and then they change frequency of I becomes frequency of I plus delta. You can give a value that you want to change the frequency by whenever I see something. Here we typically also allow delta to be negative. We can also subtract from a value. The strict turnstile part, we just have a promise that at any given time, frequency of any element will be non-negative. This will be somewhat important today. We'll see a solution that works in the strict turnstile, but not. The general turnstile is just the same here, except we don't have this non-negativity here. We just have general updates to the frequencies. Okay, so these are kind of the three variants. Okay, let me move it up so you can better see. These are kind of the three variants that people study in this field. Insertion only, just increment the count by one. Strict turnstile, update them by arbitrary values delta that are non-negative. And the last one, but then this promise that you'll never have a frequency that's negative. Right? So you can never decrement it by more than has already been increment. And then the general case at the end. So, and I'll try to, maybe the first version of this insertion only makes a lot of sense in this maybe internet monitoring example that I mentioned before, right? Whenever you want to count something, if the first model makes sense. These other ones, when you can subtract and it remains non-negative, I'll try to give some examples when we've seen solutions for where it's useful. But this is kind of the problem we want to solve. And next time we'll solve this, look at this heavy hitters problem. So this is for next time, which is maybe even more interesting. I think it's the heavy hitters. Kind of like the goal is to maintain a list of the most frequently occurring items in the data stream. So this is typically what you want to know about it. Say you're monitoring internet traffic. You want to see, is there some server now that's receiving a lot of traffic? Maybe you want to redistribute some load or something like this if you know what's popular. Maybe if you Google and they have these, I guess you can go and see what are the most popular search terms in the last 24 hours or the last day. Probably don't want to, if you don't want to log every single search term, you can also just kind of use one of these heavy hitter solutions, look at it, have a list of, try to maintain a list of who are the most popular search terms, whatever time window. So this is kind of like maintain indices by the largest. Get back to the formal definition next. But to solve this problem, we'll use this frequency estimation. This is kind of the setup, and I think we'll start out by seeing in this hash register insertion only setup, we'll start by seeing a deterministic solution, so no randomization yet. And then we'll see randomized solutions for the other two. And actually one can prove that if you want to have top linear memory in the strict turnstile and turnstile setting, you actually need to have randomization, otherwise it's not possible. It's not possible to do it deterministically. But in the insertion only, we can actually do something non-trivial even without using randomization. So let's just do that as a warm-up, also maybe to get used to this model here of streaming algorithms. So this algorithm is I guess it's called the Misra-Gries solution. So we want to be able to support scan through a list of items, and we would like to be able to estimate frequencies. So we kind of like the solution or the algorithm or data structure, or a sketch. Some parts call it sketch as well, but you're kind of sketching the stream. The solution here, I guess we need an update. But this is what happens when you see, let's see, we see one more I. We need to do something. And then we also have an estimate of I, which is supposed to return this estimate f head of I. The two different methods we need to implement. And this Misra-Gries solution is given a space budget of k. So it has a space budget. So its memory usage will always be proportional to this k that you give it as a parameter. And then the quality of the estimates will depend on the space budget. The more memory you give it, the better the estimates you get. So what is the idea? The idea is that you have so it maintains a set of counters, basically like this example up here, right, where we say the key 3 appears once, the key 1 appears 3 times, and so on. So it will store such a set of counters, but the promise is that it will never store more than k counters. So we can kind of say it stores a set of counters. Oops. Let's call it S. S is a set of counters, and the size of S is never more than k. And to begin with, S is just empty. So let's just write here, it starts out as an empty set of counters. And then we're gonna handle these updates, right? So how do we handle updates? We're gonna do basically like we did up here in most cases. So we start by if I see another I, what do? I start by checking if this is a counter. Let me write like this: I comma C is in S. So that for some count C, if there's already a counter for I, it has some value C. Then I just do the obvious thing. I just increment C by 1. Makes sense? So if I see another I check, am I already storing a counter for it? And if I am, I just increment that counter. That's the same as if you had as much space as you wanted. Okay. Else if, so what are we saying now? So there's no counter for it, but I haven't used my space budget yet. So I'm not up to k counters. Then it's also fine. I just say, well, I just saw an I. So now I'm just gonna add I, the count of 1, my set. Also makes sense. Similar to over here. Haven't seen it yet. And we saw one I, so let me just say I saw one I. Of course, the interesting part is, what if we're out of space? Right, so there's no more space in our data structure. We used our space budget, and we're not storing a counter for I among our points. So then the interesting thing is that this sketch here, what it does is it decrements all counters. Decrement all counters, and then it remove any count of 0. So this seems a little strange, but we'll try to see why is this a reasonable thing to do. And maybe we can make a small example where we try to run this. Let me show you the estimation procedure. It's very simple. Basically, we check if we have a counter for I, sub C. Then we just return that count. And else just return 0. It's a fairly simple procedure. We just check, are we actually counting this item? And if we are, just return that count. Maybe let us make a small example just to see what would happen. So let's say we give it a space budget of, say, 2. And then let's say we have a stream where we see an item 1, and maybe we see a 2, and maybe we see 3, 2, 3. Yeah, I guess this is enough for it to become interesting. Okay, let's say this is our data stream. What would happen? Right, so if we process the stream in order, to begin with, right, we see a 1. And to begin with, our set S is empty, right? So S here is the empty set. So we're definitely not storing a counter for 1, but we're not using our space budget yet. So let's put a counter for the item 1 into S. So now it becomes, maybe right like this. Now the set is C0 1, and it has a count of 1. Then we see a 2. We're not storing a counter for 2, but we still haven't used our space budget. So it's okay. So then now we have a counter for 1, and we have a counter for 2. Then we see a 3. We don't have a counter for 3. We don't have any more space yet left. So what we should do is decrement all the counters and remove those that reach 0, right? So we kind of like, we decrement this one, they both reach 0. And so now we're back to, I guess, the empty set. Then we see a 2. So now we put 2 with a count of 1. And then finally we see a 3. So then we get 2, 1, 3, 1. Okay. So this is our final S. And if we were to estimate how many ones did I see, we don't have a counter for one, so we would, yes, there were 0 ones. How many twos were there? We would say 1, but there actually were 2. How many threes? We would estimate it to 1, but there were 2, right? So we're not being exact here. We are making some mistakes. Now the question is, of course, how wrong can these estimates be? Can we give any guarantees on the accuracy of these estimates? Maybe we can just write down what I said here. So the estimate of 1 would be 0 in this case. The estimate of 2 would be 1. And the estimate of 3 would be 1. Okay. But now, can we somehow bound the difference between the true frequency and the estimated frequency? How much can they be off from one another? This is what we'll try to balance out. So, okay, so we want to relate this estimated frequency to the true frequency. Let me somehow say that it's close to the true frequency. So we want some expression involving the true frequency here, some expression involving the true frequency there. Is one of these directions easy? Yeah. Smaller than or equal to. That's right. The estimate that we get is always less than or equal to true frequency. Right? Simply because whenever we see an item, we at most increment the corresponding counter by 1. So it will never be the case that the estimates will grow higher than the true number of times it occurred. But it can, of course, become smaller, typically when we enter that case. That's when things can change. So the question is, how much smaller can it become? I think actually, maybe likely to, is the question to it, or is it a guess? I guess. Okay, I think you should think for maybe just 1 minute. Talk to the one next to you, just so everyone has a chance to think about it. So what can we say in this other direction? How bad can it be? Let me hint that it depends on this n number of times. Yeah. Okay, I think let's see if anyone wants to make a suggestion. Any ideas or thoughts on how we can relate them? Yeah.
So I think it's fi minus n divided by k, possibly plus 1 somewhere.
Yeah. sounds very cool, right? Start by writing like this.
Yeah. So the idea is to see that if we think about it, given how much we are off.
Yeah.
We are off at most by the number of times we end up in the past else case.
Yes.
And every time we are in that else case, we do one from all the entrances. And we know there are k entrances. So we have to have inserted at least k times. So
that's exactly
do that.
Yeah.
Once every, I guess, k plus 1 times.
Yes, that's actually exactly right. So let me repeat it slowly here. So that's exactly the arguments. So the thing to look at is to say, try to look at the difference between the true frequency of an item fi and the estimate fi. What happens to this difference on an update? Right? I guess how much can this change? So I guess the two cases, like either maybe we can start by looking at the case where we're updating I itself. Then if we end in this case, well, we just saw an I, but we're also changing the counter by 1, right? So frequency of I goes up by 1, the estimate goes up by 1, so the difference remains the same. If we end in this case, we also now have a frequency of 1, and the estimate will be 1. And we also just saw one more of this. The estimate was 0 before, so this goes up by 1, this goes up by 1, so everything's fine. In this case, I don't get to add a count of 1 to my I. So I saw this part here went up by 1, but this one didn't. Right, so here they move apart by 1. Similarly, it could also be the case, so it's only when we end in this last case, this difference grows by 1. It could also be that I'm updating someone else, and this difference grows, because, well, nothing changes if I'm updating some j and I end in one of the first two cases, nothing happens to the estimate of I. But if I end up in this last case, and I actually had a counter for I, then this difference grows by 1, right? Because the estimate would decrease by 1, but I didn't see any I's. So this difference in the estimate can grow by 1 whenever I enter the last case. So we want to now say how many times could it be that we enter this last case? And as was mentioned, right, the idea is that whenever we enter this last case, we must have k counters, because otherwise we would have stopped here. We have k positive counters, and we subtract 1 from all their counts. Furthermore, right, our counters, we never have a negative counter. So in some sense, if we kind of look at the sum of all our counters, then what can happen? Whenever we enter here, the sum of all the counters drops by k. Any other update can only increase the sum of the counters by 1, right? And they're always non-negative. Makes sense? So the sum of the counters is always non-negatives. So sum of let's rewrite it like this: the counter for I is always non-negative. And also the total increase in these counters throughout the whole execution of the algorithm is at most n, right? Because any update only bumps it up by 1. And whenever we end in this last case, we subtract k from these counters. So that at least gives us that the last case cannot happen more than n divided by k times. Is definitely an all about on how many times we can enter this last case. And if you're a little more careful, you can argue correctly that it can only happen n over k plus 1 times, because there has to be k operations that increase these counters by 1, then there has to be one more operation that decremented them all by k, right? So it actually does take k plus 1 counters, k plus 1 operations items in the stream to trigger this thing once, right? So if you're a little careful, you can actually divide by k plus 1 here, right? So that's the analysis, and so this is pretty nice, right? You can actually basically saying if items that are quite frequent, items that are appearing, say, more than a k fraction of the data stream times, will actually be counted fairly accurately, at least relative to the frequency. If I have someone whose frequency, it's much bigger than n divided by k plus 1. The estimate of it is a pretty good, what you call a relative estimate, like the multiplicative error in the estimate is fairly good, right? Let's say I have something, if the true frequency was maybe n half, right, and then the estimate is off by n over k plus 1, if k is maybe 1,000 or something, it's a small relative error compared to true. So it's good at counting items that occur frequently. And interestingly, okay, so maybe we can say now, what is this, the memory usage of this data structure? In terms of machine words, it is k, or order k memory words. Each of them is storing a counter and maybe the name and index into the universe. So if you're careful, you can compute exactly how many bits is it using, but as long as we say these counters, the counters use log n bits, the indices use log u bits, so on. But really, let's just say it's order k machine words for us, order k space. And actually, one can prove that if I want a guarantee like this, that is also a lower bound. Any solution giving a guarantee like this one must have a space usage that is proportional to k. So there's an omega k words space lower bound. Basically, this is an optimal way of doing this. Okay. So it's a very elegant solution. I just store these counters, subtract from all the others whenever you don't have any space for your item. Maybe let me just to motivate the next solution that we'll see afterwards. So we want to move on to this strict turnstile, so where we can have both positive and negative updates, even when we're promised, say, that the frequencies never go negative. So maybe I want to say that this solution cannot handle it, and of course, one needs to argue how would you even kind of update this this procedure to handle negative updates. It's not clear, but the general idea here is that you're always storing some set of counters, and you're trying to keep track of those. And once in a while, you evict some counters to make space for new ones. Right? So if you were to do something along those lines, when you have subtractions as well, maybe we can make a small example here. Then I think you can convince yourself that no matter how you try to tweak this, you will be in trouble if you have something like, let me say now that I see maybe 100 threes and I see 100 fours. So this is this new notation. I update the count of 3 by 100, like up there. So if you're streaming here, you'll definitely start keeping track of 3, and you'll start keeping track of 4. You'll throw out these 2 from your counters, and then maybe now, what happens if you had a 3 with a minus 100 and 4 with minus 100 is that you would have forgotten which ones that mattered, right? Which ones actually had a non-zero count. So this Misra-Gries doesn't really adapt to having negative counts because it kind of just forgets everything that's not looking like it's a heavy item. What we'll see next, these other randomized solutions can actually handle sequences like this, also so that the estimates, the errors that you get, will be proportional only to what is left in the stream. So these 2 cancel out and these cancel out. So the error we will get will only be proportional to, we have 2 items, right, with a count of 1. So it will not be fooled by these huge values that cancel out and subtract. So this is what we'll try to see a solution for next.